Okay, you might recall in the previous video on graphing exponential functions, we graphed y equals 2 times 3 to the x. Well, what happens if I change that to a negative 2? Let's find out. Again, we're going to build a table, plug in numbers. When I plug in 0, I get negative 2. I'm just going to go through these quickly here. When I plug in this, I get 3 to the 1 times negative 2. That's negative 6. I plug in 2, I get negative 18. I plug in 3, I get negative 54. Plug in negative 1, I would get 2/3, negative 2/3. Plug in negative 2, I would get negative 2/9. Plug in 3, I would get negative 2 over 27. So what's happening is we're getting exactly the same y numbers we got before, except they're all negative. That's what that negative does. So what's that going to mean for the graph? Well, it just means it's going to kind of flip it over. We get 0, negative 2. We get 1, negative 6. There. We get 2, negative 18. Way down off the graph already. We get negative 1, negative 2/3, negative 2, negative 2/9, so on and so forth. So what we get is we get pretty much the same picture that we got before, simply flipped upside down, as you can see. There's the two of them next to each other, so instead of it going up this way, it goes down that way. So the biggest change is in the range, the domain is still all real numbers. The big change is the range now is y is less than 0, and the asymptote's the same, y equals 0. So if you have a negative out in front, doesn't change the whole graph a lot. Basically what it does is it does what we call a reflection over the x-axis, which is a fancy way of saying just flip it over. Okay? All right, now input-output pairs for 4 exponential functions are listed in the table below. Complete the table. So what you're supposed to notice here, these are exponential functions, and we have our base multiplier. That's our big deal, the thing we talked about before. So when I go from 3 to 6, I multiply by 2. To go from 6 to 12, I multiply by 2. 12 to 24, multiply by 2. So each time, we're multiplying by 2, and that's what tells you you have an exponential function. When you multiply by a number each time. So the next one would have to be, multiplied by 2, it would be 48. Now, notice what's happening here. I'm going from 64 to 32. So I divided by 2, or you could think of it as multiply by a half. Or this one, 32 to 16, again, I divide by 2 or multiply by a half. So I keep following that pattern. I divide by 2, that gives me 8. I divide by 2, that gives me 4. All right, base multiplier here. To go from 2 to 6, you multiplied by 3. So the next one would have to be 6 times 3. That's 18. Multiply by 3 again. 18 times 3 is 54. Multiply by 3 again. That's 162, I think. You might want to grab your calculator and check me on that one just to make sure. All right, how about this last one? This last one we went from 100 to a 10, which means we divided by 10 or multiplied by 1/10. So I have to do that again. I divide by 10. 10 divided by 10 is 1. 1 divided by 10, well, that's 1/10. 1/10 divided by 10, 1/10 divided by 10, think of this 10 as 10 over 1, so that would be 1/10 times 1/10, which is 1 over 100. All right, so there's how we can complete a table without even knowing what the equations of the functions are, just by looking at the base multiplier and recognizing what we can do. Okay, the last thing in this section. Input-output pairs for 4 functions are listed below. Determine if each function is linear, exponential, or neither? Okay, so exponential we just talked about. We'll know it's exponential if we multiply by the same value. And then linear, remember what linear means. Linear means we have a constant slope. So something is linear if you add or subtract the same value each time. All right, so keeping those in mind, let's take a look at what we have. I'm going to start with, I guess I'll start with F, I suppose. So we go from 50 to 25, then we go from 25 to 12 and a half, 12 and a half to 6.25. Let's ask if this one's linear first. I think that's very easy to answer. Is it linear? Well, to go from here to here, we subtract 25. To go from here to there, we don't subtract 25, do we? So that one's definitely not linear. Now let's see if we're multiplying by the same value every time. To go from 50 to 25, you would divide by 2. To go from 25 to 12 and a half, take your calculator and check it. 25 divided by 2 does give you 12 and a half. If I take 12 and a half and divide it by 2, it does turn out you get 6.25. And 6.25 divided by 2 is 3.125. So this one would be exponential. And we can even say that we know the b value has to be a half. That's our multiplier. That's what we're multiplying by each time. All right, so there's the answer to the first one. Second one, is it linear? Well, 50 to 40, we subtract 10. 40 to 30, we subtract 10. 30 to 25, you only subtract 5. So that one's not linear because it wasn't subtracting the exact same value every time. We subtracted 10, but then only subtracted 5. Not linear. Is it exponential? Well, I don't think so. 50 divided by something to give me 40. If I divide that same thing again, if I take 40 and divide it by that same number, I'm not going to get 30. In fact, 50 times what would give you? 50 times what would give you 40? Well, the question mark would have to be 4/5, right? Divide both sides by 50. And if I were to take 40 and multiply that by 4/5, I'm going to use my calculator. I would have 160 over 5, which is 32. So this one's an either. It's not linear because we didn't subtract the same value each time. It's not exponential because we didn't multiply by the same value each time. That one's an either. H. Subtract 10, subtract 10, subtract 10, subtract 10, subtract 10 every time. That one's easy. That one's linear. And we would know the slope is negative 10. Finally, K. Subtract 10, subtract 10, add 10, add 10. Well, clearly not linear because we're not subtracting the same thing each time. It clearly can't be exponential either because it goes down for a while, then turns around and comes back up. We saw in our graphs that exponential functions either always go up or they always go down. They don't turn around and come back. So this one goes down by 10, down by 10, up by 10, up by 10. It can't be exponential. It can't be linear. What this one might be, this one looks like it might be quadratic because it goes down. This looks like maybe it's our vertex and then it goes back up. But it didn't ask us that. It asked us, is it exponential or linear or neither? This one's a neither, but if it's going to be something, it's most likely exponential. All right, well that finishes off this section. And we'll move on to the next section soon.